So today I'm going to be going through the start to end buildup of how you set up kind of a simple optimization problem in the particle tracking code Elegant. So I'll have a couple of slides just kind of outlining the capabilities of Elegant for anyone who might not be all the way familiar with it. And then we'll launch into two examples, or really one example in two parts where we'll look at optimizing a dog leg. In the first part, we'll go through the basic setup you need in the beamline, and then how you build up the command file and set up the objectives and optimization parameters. And then in the second part, we'll expand on this a little bit, hopefully make it a little bit more of a realistic solution in the end. So for anyone not familiar, Elegant stands for Electron Generation and Tracking. It's a particle tracking code maintained by scientists at the Advanced Photon Source at Argonne National Lab. That's very widely used in the accelerator community, particularly for electron accelerators of various types, both linear accelerators and various circular electron accelerators. Here is just a very brief summary of kind of some of the important capabilities. I'll run through. Has a wide array of elements available, many of which come in both canonical kick and matrix element flavors. While Elegant doesn't do fully self-consistent particle tracking with space charge included, it does have a few reduced models for particularly important collective effects that are relevant for electron accelerators, like coherent synchrotron radiation, longitudinal space charge, the ability to import wake fields from external sources and use those. Some of the common things you can see Elegant doing are dynamic aperture studies and momentum acceptance studies and optimization, random error studies for sensitivity analysis, and our focus for today, just general optimization problems with a built-in optimizer suite. So Elegant is often run on the command line, though today we'll be doing all of this on Radiusoft's cloud tool, Sirepo.com. That has a graphical interface that you can use to configure beamlines and entire simulations and run them in Elegant. So optimization capabilities in brief, Elegant has a built-in optimizer with both local and global algorithms available. You can optimize based on an enormous variety of just about anything that Elegant will compute as far as quantities along the beamline can be used in the optimization, as well as you can optimize directly on particle tracking, taking statistics from the bunch along the beamline. Number of helpful features we'll cover today, or at least two of these we'll cover. Built-in functions that can be used to help build up your objective function for the optimization, as well as covariables if you want to have some sort of dependent variable included in your optimizer. Finally, it also supports parallel evaluation modes, though today we'll just stick to running all of these simulations in serial. So just the general workflow that you'll see as we go through this. To start, if you are kind of starting from a blank slate to set up the optimization, we'll set up measurement locations along the beamline. And then we'll jump, and most of the work will be done setting up the command file. So configuring variables and the objective function in the command file. And then after we run the simulation, viewing results in Sirepo. So even if you're already familiar with how to do optimization configuration Elegant, this will maybe give you some of a flavor of how to set this up on Sirepo, which can be a really nice place to get started, even if you're already an experienced Elegant user. All right, so just by way of a brief overview of the problem that we're going to look at today, we're going to be trying to optimize a dog leg to be achromatic. So your simplest form of a dog leg is just two dipoles, shown in blue here, bending in opposite directions. That's just used to translate over the beamline without changing its overall direction. And in between those dipoles, you can have a wide variety of elements, focusing elements or higher order multipoles to correct aberrations or diagnostic tools. Doglegs are quite useful. Just by way of illustration down below, this is an old schematic for the RIA reaccelerator at the National Superconducting Cyclotron Lab, where you can see they use both a vertical dogleg here to bring the beam off of this platform, as well as horizontal doglegs to steer into detector holes. So as I mentioned, we'll be trying to make this dogleg achromatic. If you're not familiar with what that means, of course, a realistic bunch is going to have some energy spread around the central energy. And when you pass through a dipole, because of dispersion, you're going to have a position energy correlation in the bending plane. So we can see that illustrated here with two particles, one above the central energy, so delta greater than 0, one below, that are going to spread out in the bending plane as we go. And left uncorrected, this dispersion is going to leak out through the end of the dogleg, which is often undesirable in many applications. So what you can show is that if you set up a phase advance of 2 pi between the middle of the first dipole and the middle of the second, you can actually set the dispersion derivative to 0 at the end here and make the entire dogleg achromatic, with dispersion only existing in the middle part here. And we're going to do that initially just using 2 quadrupoles shown here at mirror positions around the symmetry point and of the same strength. I should mention the way we'll actually implement this is to set up a phase advance of just pi between the first dipole and the symmetry point so that we have a net 2 pi phase advance in the end. So that said, I'm going to switch screens here and we'll jump over to Sirepo. So this is already entered the elegant portion of Sirepo, and we're going to go ahead and actually import our first example. So I have a lattice file already prepared for this. So if I go up to the top right to the import button, you'll see if you have an existing command line or a command file, you can import that and you'll automatically be prompted then to add the lattice file specified in there and any supporting files. Or if you just want to do a lattice file, there'll be a template command file generated for you, which is what we're going to do today. So I'll import the lattice. And here we go. We're automatically taken to the lattice tab to start out with. And what we see here probably looks pretty similar to the schematic I showed before with 2 dipoles and 2 quadrupoles here. One thing to take note of is that for the purpose of the simulation, this dipole here has been split into 2 parts so that we can get the phase advance in the middle of it. So to actually take a measurement of the phase advance at the correct points in the simulation, we're going to do that by introducing 2 mark elements here. So I'm going to go over here to the new element button, select the mark element, and then we'll leave on the default name M1. And the only thing we need to do here is change this to be a fit point so that Elegant knows to include it in the optimization as a place to take measurements. We need a second fit point, so I'm going to go ahead and copy this first one. The name gets changed automatically, and we still have it as a fit point. And now we just need to insert these into the beamline. So a useful way to do that, since we need this in the middle of the beamline, I'll just select the drift right here after the middle section. We can see that gets highlighted down in the beamline editor, so we know where to just go ahead and drag and drop this mark over. You can see it appears at the appropriate position. And then we just need to add in mark 1 in between the middle of our 2 halves of the first dipole. So the goal here will be we'll measure the phase advance at each point and subtract these, and hopefully that will then be equal to pi once the optimization is complete. So that's all we need to do for editing the beamline. I'm going to go up to the top right now and start editing the command file under the control tab here. So this is the default template that gets generated for the command file if you didn't specify one already. We're going to make a couple of edits to these commands before we get started adding in the optimization. First off, for the bunched beam, we aren't actually going to do any particle tracking based optimization here, but you still always need a bunch beam command for Elegant to run the optimization. So to speed this up, we'll just set the number of particles to 1 here. And then to make things a little more interesting, I am going to modify the initial twist conditions here. Some values I already selected. So we'll do beta x and alpha x, and then identical values for beta y and alpha y here. Now, one thing to take note of in the Sirepo interface, if you set these twist values in bunched beam and you have a twist output command with matched equal to 0, these initial twist conditions automatically get mirrored over. So you can see they've already changed here. So I'm also going to go ahead and remove this track command, as we're going to be replacing it with optimize here in a moment. All right, so now we'll start adding in new commands for the optimization. I'm going to go ahead and select run control. In Sirepo, the command you select, if you add in new commands, they'll should just drop down right below that, so we can keep everything organized. I go up to new command here, and we'll start off with optimization setup. So this is kind of the top level control where you set the optimization method or algorithm. Right now, we'll just leave this on the default of simplex. This is the commonly used Nelder-Mead algorithm, the other name for it. And the only other change I'm going to make here is to just tighten up the tolerance. So with a minus sign here, this is the fractional convergence you need to see in successive iterations of the optimizer to declare that you've reached a converged solution. I'll save that, and then we're going to add in our optimization variable here. So what the optimizer is changing, and that's going to be the strength of our quadrupole. So its name is Q1. The normalized strength parameter is item K1, and then we'll set some lower and upper bounds that's allowed to vary between. I'm also going to go ahead and just adjust the step size down a little bit here. All right, so that's our one optimization variable. Now we need to set up the objective function. And generally the preferred way to do that is, if I go up to new command, is to use the optimization term command. And you can set up as many of these as you want. If you have multiples, each term just gets added together to calculate the total objective function value. All right, so we'll enter the term here. And recall we want the phase advance between our two marks to be equal to pi. And all equations in Elegant need to be in reverse Polish notation, RPN. I just need to keep in mind as I type this in. So we enter the name of the element, mark 2. Referring to these, you always need to set an instance number, even when there's just one of them. So this will be instance 1 of mark 2, and then dot, and then the quantity you want to measure there. So this will be the phase advance in x, or psi x. And then we do the same for mark 1. So M1 instance 1 dot, and then the quantity psi x. We're going to take the difference between those two, so a minus sign. I want that to be equal to pi. So we'll subtract pi from that, and then to make sure that our minimum occurs at 0, we're just going to square this entire quantity. All right. And then the final thing, to set up the optimization, we need a optimization, or just an optimize command here at the end, which will actually initiate the optimization run. So this is the basics, all that you should need to set up the optimization. We're going to add in a few more commands now, since we also want to be able to evaluate what the result looks like at the end, all in the same simulation. So to do that, I'm going to go up to new command and now switch over to the advanced tab, as we need to save lattice command. And I'll select the file name for that. And what this is going to do is actually save the final solution lattice that was found by the optimizer, so that we can rerun it now and see how it looks. We'll need another run setup command here. So back to basic commands and select run setup. We'll change over to the saved lattice. And then the only other thing I need to do here is the momentum defaults to 0, which Elegant won't like, even though we aren't doing any particle tracking. So I'm just going to set that to the same value that we have up in the first run setup command, just for consistency. All right. And then the other thing we need to see is the twist output at the end here. So I'll select a new twist output command, make sure that's being saved to file. This name will be automatically updated when I hit save changes. I am going to turn matched off because we don't want this to be a periodic cell. We're going to set our own initial conditions that are the same as what I entered previously here for beta X and alpha X, and then also vertically. Okay, and that should be it. We should be good to go here and run the simulation. So to do that, we'll go up to the top right to the visualization tab, which is also where we start the simulation. So I'll go ahead and do that. Hopefully this will just take a few seconds. All right, and looks like it completed. To run, you'll see a number of little drop-down menus here. Each one of these just corresponds to a file that was produced during the simulation. And you can edit these to plot various quantities from the file. So first off, we'll look at the first twist output command. So this is taken prior to the optimization happening. And we'll just go ahead and plot the dispersion in the bending plane, which is the quantity eta x here. And not surprisingly, we can see that this just grows over the course of the beamline, and it does not go to 0 like we want at the end. So hopefully now when we go over to twist output 2 and plot this, we'll see that eta x goes to 0 at the end after the optimization has completed. So I'm also going to plot the derivative of the dispersion, eta xp, and I'll turn on a lattice overlay just so we can see how this looks along the beamline. And we can see we've reached the result that we want. Here now at the end of the beamline, if I click on this last point, brings up we've reached eta x and eta xp are both 0 to machine tolerance at least. So this looks really good. We've accomplished the goal we set out to in terms of making the beamline achromatic. But now we can ask, is this a reasonable solution? And how do other quantities of the beam look, like the beam size, for instance? So I'm going to go ahead and plot beta x and beta y, which will correspond to the beam size here. And we can see that we do have a problem here. Beta y is blowing up to several thousand meters here, and likely that means that our beam is going to get way too large vertically for this to be a realistic solution. So now I'm going to jump over to the next part where we're going to add in a few new variables and another optimization term to try and fix this. So go up here to simulations, which will bring me back to my menu. And I've already got the start of this uploaded. So we'll jump into that. It automatically brings me into the source tab, which we don't need to worry about since we aren't doing particle tracking. So I'll move to lattice. And now you can see that we've added in a few new features to our old beamline. So now there are 2 additional quadrupoles on either side of the symmetry point of the dog leg. And the other thing to take note of is that I've now actually added in some new drifts here. So on either side of the second quadrupole, we have drifts D2 and D3. And the idea here is that we're going to not only vary the quadrupole strengths of all 3 quadrupoles, but we're going to let the position of quadrupole 2 on either side move around. And when we do that, we want to make sure we don't change the length of our beam line. So we want to keep the total length of drift 2 plus drift 3 to be constant. And the other thing I'll mention, I did also, since I know roughly what the answer is going to be, just to make this a little faster, I have set some values already for the quadrupoles to put them kind of close to the solution that we want to get here in the end. Though with a little bit of work, you can find the solution even without that. All right, so over in the command tab, to start out with, this is exactly the same state that we had at the end of the first example. So we still have our optimization variable for the first quad and our term to set the beamline to be achromatic. And now we're going to go in and first off add in the two new quads, which should look pretty familiar now. This is exactly the same thing as with quad 1. So just Q2. I'm going to set just the same bounds in this case and the same step size. And then likewise for quadruple 3. Optimization variable for quad 3. Strength parameter. Exact same bounds. Okay, so the next part, we need to actually set up the drifts that I was talking about. So we're going to let drift 3 be our independent variable in this case. So we'll assign it to a new optimization variable. The element name is D3. In this case now, to vary the length, that'll be the quantity L. And we're going to set a finite lower limit since we don't want two quads running into each other. And for the upper limit, just to make sure in the end that drift 2 doesn't become 0, we're going to set the maximum a little bit lower than the total length of D2 plus D3, which is 0.9 meters. Right, so the optimizer will be varying D3, and we want to make sure then that D2 is varied in kind so that we keep the sum of the lengths for D2 plus D3 to be a constant. So to do that, I'm going to go up to new command, select again the advanced tab, and go down to optimization covariable. Now, covariable is going to be for element D2, also the drift length, and then the equation governing this, which again is going to be an RPN equation, is going to be the total length, which is 0.9 meters. Then minus the drift length for drift 3. So as the optimizer updates drift 3, drift 2 will be set to maintain this 0.9 meter total distance. All right, so that takes care of all the updates we need to make to the optimization variable. The last step here now is to add in a new optimization term that's going to hopefully help constrain the beam size. So to do that, I'll go up to new command. We'll just go back to basic and add in a new optimization term. Here we're going to make use of one of the built-in functions that Elegant has, which is the soft edge greater than, which is SEGT. And what this is going to do is provide a penalty if the parameter you select becomes greater than some threshold value. So the parameter we want is the maximum beta y along the beamline, and that's represented just as the statistic, so max dot quantity, which is beta y in this case. Let me separate these out a little bit. And then we'll make our threshold to be 50 meters and beta y, and then you need to assign some penalty growth rate. So we'll do 0.01 for that. All right. So this term should hopefully then add a large increasing penalty if beta y exceeds the threshold. And I think that should be all we need to do. We've updated our variables, we've added in a new term, and then the rest of this will just stay the same. We can keep the same final output to evaluate the lattice here at the end. So we'll go ahead and try running this. Start new simulation. All right, and we'll go over, just jump directly into the final evaluation of the optimized beamline here under twist output 2. And first off, we should check and make sure that we still have that achromatic condition, since that was our primary goal here to start. So we'll plot eta x and eta xp. See, the overall form between looks a little bit different, but just as we wanted, in the end, we reach 0 again for these. So we have an achromatic beamline. And now we can see if we've now managed to constrain the beam size vertically with these new quads and new condition. And you can see what we have. The vertical beam size shown here in orange, that's beta Y. And we've even stayed a little bit below that bound of 50 meters. And we now have a very nicely constrained beam size along the beam line. So we've achieved our new goal here. Right, so that brings us to the end of the example demonstration. So I'm going to switch back to the last slide here and go ahead and open things up for questions.
Awesome. Thanks, Chris. I appreciate that wonderful presentation. We've got a couple different questions queued up here for you. The first question is, how do you know what to set the optimization variable step size to?
Oh, okay, that's a good question. I'll jump back. I think we'll stick over here so people can see what's being referred to. Here's one of the optimization variables. So yeah, as I mentioned, I did change this default step size away a little bit. There isn't any real qualitative, exact quantitative way, I should say, for setting this that I know of, but you do want to be a bit careful to make sure that it's not wildly either smaller or on par with the kind of size of your limits. If you set this really small, even though it does get varied eventually, you may find that if you don't have enough total evaluations available to the optimizer, it may not make much progress towards finding a minimum. Whereas if you set it very large, you can get very, very strange things happening where the optimizer will stop prematurely. So it's something just to keep in mind, especially if you're looking at values with that are significantly larger or smaller than kind of the default of 1 here. That can be a good thing to change if you aren't seeing convergence.
Awesome, thank you. Our next question is, achromatic means the zero dispersion at the exit of a dipole?
Yes, that's correct. The zero dispersion at the exit of the second dipole in this case, since we care about the entire dogleg being net achromatic in this case. So independent of the energy.
Great, thank you. And then we have one more lined up here. Question is, how do you set up parallel optimization?
Okay, so I can sketch out a little bit about that. So the main change you're going to make in terms of the command file, which right here, is, of course, we showed just the optimization setup command here. If you want to enable parallel optimization, there is a separate command that would go in place of just plain old optimization setup. So Sirepo, if I go up to new commands, might be under advanced. Yes, it'll be parallel optimization setup. Obvious. And if we click that, so most of this, you'll actually see kind of a superset of the regular optimization setup. So a lot of the same things in terms of tolerance and setting up various parameters for your optimizer. Though now you'll also see that the list of methods though has changed. You still have simplex, which is available, but there's also a few other methods that can be run in parallel. And depending upon if you're doing particle tracking or not, will kind of change how the parallel optimization proceeds. You can either configure it so that you run a single evaluation at a time, where all the tracking is done in parallel, or you can have, if you have small numbers of particles or aren't doing particle tracking at all, you can have every processor running a separate evaluation all at once. So that can be useful if you're doing something like swarm optimization. Every processor just gets its own individual in the swarm. If each of the evaluations can be run very quickly.
Thank you. Next question coming up. Do you need 6 quads to achieve this? I'm not sure what this means, but I hope you do.
Yeah, so the question. I believe you do end up needing, you may not necessarily need 6. if you want, you do want the beamline to be symmetric in the end. And so you can probably accomplish the achromatic condition actually with just, perhaps with just a single quad placed in the middle, and then 2 additional quads to provide focusing. Though I took kind of the easy way out here, and since I knew this was already a solution that works well, and that I've used in an existing beamline design.
Great. Well, we are out of time with that last question. So, oh wait, we got one more. This is from Samira, and they're asking, can you see how the beta functions change with energy?
So in this case, not easily in this example, what you would end up probably having to do is set up some sort of parameter scan on top of this where you actually vary the beam energy. So I probably don't have time to go through setting up a parameter scan, but yeah, you can do that with the vary element command. And then you would end up varying the actual beam energy while keeping the central energy of your beamline constant in that case. I think might be, it sounds like what you want to do. But that would end up being a little bit more involved than what I can probably run through in a minute or two.
All right, thank you. We are just a couple minutes over time, so we'll wrap it up for today. Thank you everyone for attending the Radiosopht webinars. We'll send you a follow-up email this next week that includes a link to the recording of this webinar. And I hope you'll join us in April for our next version. Thanks everyone. Have a great afternoon.